All right, ladies and gentlemen, class recording has started. So, starting off, calendar. Where's that coming from? Where's that coming from, teacher? Just randomly, right in the middle of class. Couldn't wait till, like, in between classes or something. Let the record show that Miss Dietrich brought back one of the 3 stools that I lent to her. Okay? So yeah, she was having trouble sitting because of her hip, and so I lent her some stools. So, but I did lend her 3 stools, and now I've gotten 1 back. So, yeah. All right. Calendar. On Friday, we started in on the inclined plane and talked about how we handle 2-dimensional forces at the inclined plane. We will continue on with that today. We will do another practice problem where the object is in equilibrium. But then the second problem we'll do is now where they're not in equilibrium and what happens if the forces aren't balanced, and we'll go from there. Tomorrow, for block, we will do lab related to the inclined plane. We're back to the coefficient of friction, but now we're dealing with it on the inclined plane, and we'll talk a little bit more about how we do that tomorrow during lab. Then on Friday, we'll wrap up the inclined plane, do another example problem where there's some acceleration. Then next week, Monday, we will wrap up forces in 2 dimension, do a couple more example problems, and then test on Tuesday. So test 1 week from today. Questions about the calendar? All right. First problem that we're going to do today is from the review of Chapter 7. It's on page 171, and it's problem number 36. It's off of page 171, problem number 36. It says, you push a 325 Newton trunk up a 20-degree inclined plane at a constant velocity by exerting a 211 Newton force parallel to the plane's surface. Then there are 4 parts, but one of the things I don't necessarily like about your book is that they give you these 4 parts instead of just saying, hey, solve for this. So I'm going to break protocol a little bit. Okay, sorry. Can you guys read that or no? You can't hear it. So here, I'll make it a little bigger. All right. So it says, I'm going to break protocol a little bit. Instead of starting with what we are looking for, because there are 4 things this question is asking you to look for, let's jump straight ahead into things that we know. All right, so what information have they given us here to help us solve this problem? So what's one thing they gave us? Did they give us the mass? Okay, they gave us the weight, right? If it says a 325 Newton trunk, they gave us the weight. And we said that a fancy name for weight is the force of gravity. So we know the force of gravity, right? So keep that in mind, and we'll switch that in the second problem today just to make sure that we have an example of both. Okay. All right, other things they gave us.
Degree of incline.
Okay, they told us that this ramp is inclined by an angle of 20 degrees. So theta in this problem, 20 degrees. Okay. Other things they gave us? Not normal force in this case. This is an applied force, right? If it says that you're exerting a 211 Newton force, that's an applied force, right? You're pushing that hard, right? And then there's one more thing in the problem that's going to help us out. It's not necessarily a measurement, but it's definitely something that we know that's going to help us get to the end of this problem, and that's what? That's going to help, but that wasn't what I was thinking of, actually. This part here, the constant velocity part, because that means we're in equilibrium, right? And if we're in equilibrium, we've discussed on numerous occasions that in 2 dimensions, we have to have equilibrium on both axes. All right, good there? Questions? Okay. We have what they gave us to work with. Now let's draw ourselves a picture. So, my shapes, here's my inclined plane, here's my trunk, else before really needed to have somebody actually pushing it. So there we go. It helped their mental picture. So, all right. Forces that are acting on this chunk. Where are we going to start? Okay, so gravitational force. Gravitational force, we said, always acts in which direction, regardless of the surface? Gravitational force is always going straight down. Regardless of what the surface is like, gravitational force is always going straight down. And they gave us gravitational force in this problem, right, of 325 newtons. What else? Okay, they gave us an applied force, right, and it tells us that the applied force is parallel to the plane surface. We can assume that if this crate is moving up a 20-degree inclined ramp, which way are we going to probably have to apply the force? Up the ramp. So there's our applied force. All right. And we know that our applied force, 211 newtons. What else? What else did they give us to work with? Oh, actually, they didn't really give us work with, but some other things that we can assume here. What other force do we know is going to have to go on here? Okay, normal force. We said normal force is one of the ones that's definitely affected by the fact that our plane or our surface is now inclined, right? Because our definition says that normal force always acts how? Perpendicular to the surface, right? So that means that in this case here, normal force is going to go something like that, right? Will normal force be equal to gravity in this problem? They don't point opposite of one another, so they can't cancel each other out, at least not one for one. Okay? And then, even though we didn't go through this problem here, right, letter D is asking you for the coefficient of friction. If there's coefficient of friction, that means there's probably what also acting on this object? Frictional force, right? If this object is moving up the ramp, which way is frictional force going to have to be acting on it? Down the ramp. So even though we don't know what it is just yet, we can put frictional force in like that. All right. Good so far? Questions? All right. Here's where this problem became different from the problems that we've done before, right? We said the real key to doing these problems, to make them a lot easier, is if we rotate our x and y axis. We said we were going to make the x-axis parallel to the ramp surface itself. And then the y-axis will be perpendicular to the ramp surface itself. If we do that, what do we see about red, blue, and purple? They're all on the x and y axis. Do they have components? No. They do not. But now gravity, because it acts straight down, is gravity on the x or y axis of the coordinate system that we've chosen now? It's not. So it has components. Components always run along the axes of the system, or the coordinate system that we chose. So there's a component like this, and then there's a component like that, right? But we talked about moving that component down here like this, right? If this component is perpendicular to the ramp, and this component is parallel to the ramp, that means that has to be a right angle. Okay? And now we've made ourselves a nice little right triangle. But if we're going to find components, we need to know what about that right triangle? We need to know a side, which we have. We also need to know an angle. We said that if we know that the ramp is inclined by a 20-degree angle, that means this angle right here, the one between the new perpendicular to the surface axis and the actual gravitational force, also has to be 20 degrees as well. The you don't believe me, I'll show you later. I know. Nobody asked, so I assume I'm just trustworthy. So. All right, but now we have a right triangle where we know a side and we know an angle, and we can find the other two sides. Let's do that. Let's find the other two sides of that triangle. In relation to that triangle, right, we said because we're finding the components of gravity, it's important that we make sure that gravity is the hypotenuse of that right triangle. Right? Don't make any other triangle. Make sure that gravity is the hypotenuse of that right triangle. Those two sides, 305.4 and then 111.2. So as far as naming convention goes, right, we talked about that this component, the 305.4, we generally refer to that as f of g perpendicular, because it's that component of gravity that's perpendicular to the ramp. And that means that this component here, we generally refer to as f of g parallel, because it's the component of gravity that is parallel to the ramp. In essence, we said finding the component vectors of this gravity is basically like getting rid of all of this stuff, right? And just leaving us with those two components. With that being the case, we can start filling in some other parts of this picture. For instance, what do we know about normal force in this picture now? Normal force has to be 305.4 newtons. Because if we look on the y-axis, how many forces are there on the y-axis? There's two. 1 points up, 1 points up, 1 points down. They got to be equal to one another. If you look at the parallel axis, right, or if you want to call it the x-axis, whatever, how many forces are there parallel to the ramp surface in this picture now? There are three. There is the applied force going up the ramp, but then the parallel component of gravity down the ramp, and frictional force also down the ramp. Based on the information we have, can we figure out what the frictional force is? Should be able to, right? What are you going to do? F of A minus f of g parallel, right? And then the difference has to be whatever's left over has to be friction, because what has to be true on the x-axis? Got to end up 0. And when you do that, I think you end up with 99.8. Is that correct? Okay. All right. Now that we know all this information about this picture, let's go back up to the actual questions and start answering them. First, what is the component of the trunk's weight parallel to the plane? We labeled that f of g parallel. And we found out that f of g parallel is 111.2. That's the component of the trunk's weight parallel to the plane. Good there? B, what is the sum of all forces parallel to the plane's surface? In this case, because we have constant velocity, that means we have to have equilibrium on both axes. So what has to be the sum of all forces parallel to the surface? 0. C, what are the magnitude and direction of the frictional force? Well, we know frictional force we calculated to be 99.8 newtons. Technically, on that x-axis or on that parallel axis, there is a positive direction and there is a negative direction. but it gets a little confusing sometimes because some people want to call up the ramp positive, some people want to call down the ramp positive, some people want to call whichever way the object is moving positive. Just gets kind of confusing. So as far as the direction goes, why don't we just go down ramp? Okay? And then we don't have to worry about positive or negative or whatever. And then the last one, part D. What is the coefficient of friction? In order to figure out the coefficient of friction, how many things do we need to know? You know two things, right? You need to know the force of kinetic friction, and then you need to know the normal force. Do we have both of those things? We do. So based on that, we should be able to figure out what the coefficient of friction is, and if I know math, it should come out a little bit less than 0.33. 0.327? All right, good there? All of the problems off of the green sheet that I gave you on Friday are all equilibrium problems, an object moving, no acceleration along the ramp. But that's not always the case. So let's increase degree of difficulty here a little bit, and let's take a look at we are going to go to page 153, and we're going to look at this example problem on page 153. Make that a little bigger. Page 153. This is an example problem that's from the book, so they actually work out how to do it in the book, but they skip over some steps, I think, sometimes, and don't exactly explain why they're doing stuff, so why don't we go ahead and take a look at it. All right, so it says, a 62-kilogram person on skis is going down a hill sloped at 37 degrees. The coefficient of kinetic friction between the skis and the snow is 0.15. How fast is the skier going 5 seconds after starting from rest? FYI, this problem is jumping in the deep end, just so you know, right? They did not, as far as an example problem goes, they did not give you a very easy one to start with. But it's nothing we haven't done before. It's just putting a lot of pieces together. So with that in mind, let's go through the process. What is this question asking you for? It's asking you for velocity, right? And that's the how fast part. But there's another keyword in there that should tell you which velocity. It's final velocity, right? Because it says how fast after, right? So this problem is asking us to solve for final velocity. And you might be saying to yourself, wait a minute, I'm going to solve for final velocity in like 2 months. Guess what? You're going to have to do that, all right? Meaning, there's probably some other information in here, right? So, what other things did they give us to work with in this problem? Okay. They gave us the mass of this. They gave us the mass of the person, 62 kilograms. Okay. What are some other things they give us to work with in this problem? Okay, they give us the angle, right? They give us that the slope is inclined 37 degrees. They gave us the time over which this person is skiing. Right. They gave us the initial velocity starting from rest. And then, one other thing they gave us the coefficient of friction being 0.15. All right, good there? Okay. This being the case, based on the information that they've given to us, especially the part that I've written in black over here on the left, what is this kind of looking like now? This is looking kind of like a kinematic equation problem. But in order to do a kinematic equation problem, how many things do you need to know? 3. And how many do we know? 2. Right? Because we don't know this one. We're going to solve for that one. We need to know 3 things. We've got 2. We have a couple more options, right? What are our other options that we could theoretically know to help us get final velocity? Acceleration or displacement. Those are the only other 2 things that we could find to solve a kinematic equation problem to get us what we need to know. Good there? Alright, so, picture. In order to make sure that we are taking care of all our bases, right, I'm going to flip this one around and make my person, my skier, go down the hill this way. So, person, skis, pulls, right, whooshing, definitely chilly outside, so we're going to need a hat here, right. We'll group all that together. There we go. It's probably more work than it's worth, but whatever. Okay. All right. Forces. Forces acting on the skier. Where are we going to start? Okay, let's start with gravity. Okay. In the last problem, they gave us the gravitational force. In this problem, they did not give us the gravitational force, but they did give us the mass, and we know how to handle that, right? No problem. So you plug that into your calculator, and you find out that the gravitational force. You find out that the gravitational force acting on this object is what? 608.2. Yeah. All right, other forces that are acting on this skier. What else can we put forces acting on this skier here? Okay, friction, right? If this object is going down the ramp to the left, friction's always got to go opposite, right? So we'll take friction and we'll put it right in here. We'll label that as FKF, right? And then one more force here, normal force. We said normal force is really one of the keys to doing this problem. Normal force always perpendicular to the surface that causes it. There it is. And we'll label that as F of N. Okay, good there? So, we said the key to doing this problem, rotate the x and y axis. So, there's my x-axis. I'm just going to move that up a little bit. Yikes. There's my y-axis. Okay. And, much like we just did in the last problem, right? Gravity not on the x-axis or the y-axis, so it has components. Yes? Here, one component that points this way, perpendicular to the incline. One component points this way, parallel to the incline. Right? Move this down here. Extend that a little bit. Right? Because they're one on the x-axis, one on the y-axis, they have to be perpendicular. Okay? Then 37 here, that means 37 here. All good? Everyone understand where I got that from? Right? Alright, now we've got ourselves a right triangle where the gravity is the hypotenuse of that right triangle, and we can figure out the other 2 sides. Go. Here. 485.7, and that's going to be my f of g perpendicular, right? And then parallel? 377.0, that's fine. 366 does sound more familiar. So.
Oh yeah, that's what I meant.
So 366, and that's going to be my f of g parallel. All right. Now, based on that, I can get one thing directly. What's my one thing that I'll know directly here? Normal force. Okay. This is going to be 485.7. Can I automatically assume that my frictional force is 366? No, because it is not an equilibrium problem, right? But if I've got the normal force and I've got the coefficient of friction, can I find out what the frictional force is? Right? You know that coefficient of friction is equal to frictional force over normal force, right? That's what our definition of coefficient of friction is. We know that this is 0.15. We don't know what this one is, but we do know that this one is now 485.7. And from that, I can figure out what the frictional force is. Tell you what you get for that?
72.9.
What you get?
Yeah.
That turns out to be 72.9. Good? All right. We said that in order to solve this problem, over here, I got to know one of these two things. I either got to know the acceleration or I got to know the displacement. Remember any formulas that have acceleration in them? Like really important formulas that we use a lot? That, you know, one of the fundamental laws of the universe. Alright, sigma F equals M times A. But in this problem, where is the acceleration occurring? Parallel to the ramp or perpendicular to the ramp? Parallel. So we only want acceleration that's parallel. If we only want parallel acceleration, we only want parallel forces, right? How many forces are there parallel to the ramp in this picture over here? There are two. There is f of g parallel plus FKF has to equal the mass times parallel acceleration. All right? Important thing being, what do you see about the f of g parallel and the friction in this problem? Which direction do they point? Opposite. They're opposite, right? So what are you going to have to do to those two numbers? Subtract them, basically, right? You're really adding a negative number, but it's still subtracting, right? So 366 plus negative 72.9 has to equal 62 kilograms times the acceleration. Bell's going to ring, but once you find the acceleration, what are you going to do? Bring it up here, solve the kinematic equation for V final. Like I said, deep end. But nothing that we've ever done before is put it all together. Tomorrow we're back on lab. And looking more at some of these things as far as the parallel, perpendicular components and all that good stuff, right?
Shannon?